We're continuing to work through 3D particle equilibrium problems. The previous problems we worked, I kind of gave you the vectors in spherical coordinates or direction cosines, but a lot of 3D particle equilibrium problems use cables or links. And so you have to get really good at writing forces along cables. In other words, writing the unit vectors along cables. And so the rest of these examples will be cables. This is a pretty easy problem that's a good test problem. What we have is a 400 Newton cylinder hanging from a point at A. There's three cables. There's AB, which lies in the XY plane. Well, AB is parallel to the x-axis. Cable AC, which is parallel to the y-axis. And then you have cable AD, which has X, Y, and Z components. And this problem might ask you to find the tension in AD. Well, you should be able to look at this and realize that AB does not have a Z component. AC does not have a Z component. The only one of these three ropes that has a Z component is AD. And so if I can find the Z component of AD, then I can write a Z equation to get TAD. So let's write our vectors. So our TAD vector, well, this is our free body diagram. So I've got TAD, I've got TAB, TAC, and then I have the weight acting down, which is 400. My TAD vector is equal to the TAD magnitude, and then the line vector from A to D. As I go from A to D, I go -2 in the X, -2 in the Y, and then +4 in the Z as I go from A to D. So -2, -4, and 4. That's the line vector. So the numerator here is the line vector. I want to take the line vector and divide by its magnitude. And so the magnitude of this guy is the square root of 2 squared plus 4 squared plus 4 squared, which is 16 plus 16, which is 32, plus 4, which is 36. Square root of 36 is 6. And so the line vector divided by 6 gives me the unit vector. And so -1/3 in the X, -2/3 in the Y, and 2/3 in the Z. It's easier to just use the unit V function on your calculator. So if you actually go to your calculator, either the TI-89 or the Inspire, we can just go to Catalog, click on U, click down to Unit V, enter, Unit V, Control to get square brackets, and we get -2, comma, -4, comma, 4, enter. And that gives me the unit vector, which is -0.333, -0.667, and +0.667. One more function on the calculator that helps you is calculating the square root of the sum of these squares is the norm function. And so if you go Catalog, N, and scroll down to norm, enter, square bracket, 2, comma, well, it doesn't matter, 4, comma, 4, enter. And it gives you the norm of this guy, which is 6. So once we have the unit vector for TAD, we can sum forces in the Z direction, and we get 2/3 of TAD minus 400 is equal to 0. This guy does not have a Z, this guy does not have a Z. And I get TAD is equal to 3/2 times 400, which is 600 newtons, which is this guy. And likely that's the only question an exam question will ask. But you can go on from that. You can sum forces in the x direction. And the x component of this guy is minus 1/3 TAD, which is 600, plus TAB. And so TAB is equal to 200. And then in the y direction, I've got negative 2/3 of TAD plus TAC is equal to 0, so TAC is equal to 400. So pretty simple problem, one step to get TAD, makes a good exam problem or final exam problem. And so you should be able to recognize this guy and know how to enter this into your calculator, get the unit vector, use unit V, use norm, and go from there. Here's a slightly harder 3D problem, but still not too bad, in that I've got 3 cables, but TAD and TAC are symmetric about the XZ plane, because this is 8 and 4, this is 8 and 4. And so, and if you should be able to recognize that they're symmetric. And so if they're symmetric, then you should be able to write instantly that TAC is equal to TAD. But let's work it out. Let's just show how you do that. So TAC vector is equal to TAC magnitude. The numerator here is the line vector from A to C. As you go from A to C, the change is minus 3 in the x, minus 4 in the y, and 8 in the c, in the z. So minus 3, minus 4, 8 is the line vector from A to C. Then you want to divide that by the magnitude or the length of that line, which is the square root of 3 squared plus 4 squared plus 8 squared. 8 squared is 64. 4 squared is 16, plus 64 is 80, plus 3 squared, which is 9, square root of 89, which is 9.434. So you can find this in your own conventional way, or you can use the norm function on your calculator like we did. Or you can just use the unit V function. So again, we can go unit V. I'll just show you that again because it's so easy. So catalog, U, one step down is unit V, square bracket, minus 3, comma, minus 4, comma, 8, enter. And we get negative 0.318, negative 0.424, and 0.848 is my TAC unit vector. My TAD unit vector has the same terms, except it's a negative 3, it's a positive 4, and it's a positive 8. So it's very similar. And so I end up with a negative 0.318, a positive 0.424, and a 0.848. So this is my unit vector for AD. If I write the y equation, I get negative 0.424 TAC plus 0.424 TAD is equal to 0. The 0.424s cancel, and you basically get TAC is equal to TAD, which you should have recognized already. Then we can sum forces in the z direction. And this is a 60-pound, 60. And so in the z direction, I have a 0.848 times TAC plus a 0.848 TAD minus 60 is equal to 0. This TAB does not have a z component. And I can solve for TAD is equal to 35.4 pounds. And that's equal to TAC, which is 35.4. And chances are, if this is an exam problem, we would be done because the problem might ask for one or the other of these. And you basically have to solve for both of them together. If you wanted TAB, once you find these two, then you can sum forces in the x. And I got TAB minus 2 of 0.318 times TAC or TAB, there's two of them, and just plug in 35.38, and you get TAB as 22.5 pounds. And so this is a problem, 3D problem, involving symmetry, where these two guys, you know they're going to be equal from one another, which again simplifies the problem a little bit and saves you from using a matrix.